Welcome to the deep dive. Today, we're taking a shortcut to being truly well-informed about, well, a really fascinating part of modern construction. Cross-laminated timber, or CLT, floor and roof analysis.
That's right. We're going to pull back the curtain a bit on the design process. We'll tackle some of the real questions designers face, day to day. So you get an insider's perspective on how these incredible mass timber panels get engineered, not just for safety, but also for optimal performance and even the comfort of people using the building.
Right. Comfort is key, too.
Yeah.
Our mission today is to transform what might seem like pretty dense engineering into, well, surprising and digestible insights.
Like that.
We'll uncover the clever ways designers make sure these beautiful mass timber floors stand strong, feel solid underfoot, and perform beautifully over time. Okay, let's unpack this. So to kick things off, let's maybe get a picture of what we're even talking about. When we say a generic mass timber floor system, what are the core structural bits, the main players?
Yeah, good place to start. Imagine you're building with these giant engineered timber planks. At the heart of it, you have the CLT panels themselves, big, solid wood panels.
Okay.
Then these are typically supported by larger beams, girders, and maybe smaller ones like purlins or joists.
Right, like a grid underneath.
Exactly, which in turn rest on columns. And often you'll have a really robust core wall, maybe concrete or more mass timber, providing central stability. It holds the whole system together.
Okay.
These elements work together, kind of like a sophisticated timber skeleton for the floor or roof.
That gives us a really clear picture. So when designers first approach these systems, what's their initial thought process? How do they start to, get a handle on the forces involved?
Well, for forces that mostly push down in one direction, we call that one-way spanning behavior, which is pretty common. Designers often simplify things. They'll analyze a major span direction almost like it's just a simple beam.
Ah, okay.
And a really convenient way to start is to just consider a 1 foot wide strip of that big CLT panel.
Just 1 foot wide.
Yeah, just a slice. And this trick, it's actually quite versatile. You can use it to analyze panels that span across multiple supports or ones that stick out like cantilevers or, other more complex setups.
All right, so they're treating a slice of the panel like a basic plank. Smart. Now, the big question, how do engineers make absolutely sure a CLT panel is strong enough? Strong enough to hold everything up?
Okay, yeah, the fundamentals. The very first and probably most critical check is for flatwise flexural strength.
Flexural strength.
Right. It's all about the panel's ability to resist bending forces. Think of like a diving board you wanted to flex a bit, but definitely not break.
Makes sense.
So let's maybe use a common scenario, say a 15-foot span floor. It's carrying a typical live load people, maybe some movable furniture, and also a significant dead load from the building's own weight, partitions, finishes.
Standard stuff.
Pretty standard. Designers calculate the maximum bending force the moment that the panel will experience under those loads. For our example, let's say it comes out to, around 3,500 pound-feet per foot of width.
Okay, 3,500.
Then they compare that number to the panel's inherent bending capacity. Now, this capacity, it depends on the strength of the wood used in the outer layers and something called the effective section moduluses.
Section modulus.
Yeah, but it basically quantifies how efficiently the panel's shape resists bending. For a common 5-ply CLT panel, this capacity might be closer to 4,000 pound-feet per foot.
Ah, so higher than the expected load.
Exactly. As long as the applied force, that 3,500, is less than the panel's capacity, the 4,000, it passes the bending strength check. It's good to go for bending.
So it's clearly strong enough to resist that bending force. Okay, but I imagine there are other forces, right? Like shearing. Is that a big concern too?
Absolutely. You nailed it. The next major check is flatwise shear strength. You might also hear it called planar shear or out-of-plane shear, sometimes even rolling shear.
Rolling shear.
Yeah, imagine trying to slide one layer of the wood within the panel past another layer. That's the kind of internal force we're checking.
Okay, I can picture that.
So back to our 15-foot span example. The maximum shear force might be, say, around 940 pounds per foot. Now, our typical 5-ply CLT panel, the one we're using, it would probably have a reference shear capacity of over 3,000 pounds per foot, maybe like 3,025.
Oh, wow. That's a huge difference.
It is. Since the applied shear, 940, is much, much lower than its capacity, 3,025, it's well within safe limits. There's a big margin there. This check ensures the panel won't fail by, delaminating or shearing internally.
Okay, so it won't break under bending, and it won't break under shear. We've established it's strong. But a floor needs to feel right too, doesn't it? What if it sags too much or feels, I don't know, bouncy when you walk on it? How do designers deal with those factors, the human experience stuff?
That is absolutely critical, and that's where deflection calculations become really, really important. Even if a panel is super strong, too much sag, too much deflection can cause problems. Aesthetic issues, problems with floor finishes, or, like you said, just making people feel uneasy.
Right. Nobody wants a floor that feels like a trampoline unless it is one.
Exactly. So for our 15-foot span, let's say the initial calculation for deflection purely due to bending might come out around 0.4 inches.
Okay, 0.4 inches. That sounds pretty small, actually. Is that the whole story, though? Or are there other things, maybe less obvious things, that add to that sag?
You've hit on a really crucial point. And this is where CLT gets particularly interesting compared to maybe some other materials. While that bending stiffness is important, for CLT specifically, shear deformations can be surprisingly significant.
Shear deformations. So the shear affects the sag, too.
It does. When we actually account for the shear stiffness in our example panel, it adds maybe another 1/10 of an inch or so to that initial 0.4 inches of bending deflection.
Wow, really?
Yeah. So suddenly you're looking at maybe 0.44, 0.45 inches total immediate deflection. This means shear deflections can often chip in, maybe 10 to 20% of the total sag. It's a detail designers absolutely cannot overlook.
Huh.
Ignoring it would mean underestimating how much the floor will actually deflect right after the load is applied.
That's fascinating. That something seemingly subtle, like internal shear, can add that much noticeable deflection. Okay, but floors are in buildings for decades, right? What about long-term effects? Like furniture sitting there for years, does that make the sag worse over time?
Great question. Yes, that's another layer we absolutely have to consider. It's called deflection creep.
Creep, okay.
Timber, like, many materials actually,
Right.
can slowly deform or creep over time when it's under a sustained load, like that heavy bookshelf you mentioned.
Right.
For CLT used indoors in dry conditions, designers typically apply a creep factor. Usually this factor is 2.0.
So it doubles the effect of long-term loads.
Essentially, yes, for the long-term portion of the load. So in our example, the immediate sag from short-term loads, people walking around, is fairly small. Let's say it's about 0.18 inches.
Okay.
But the immediate sag from long-term loads the structure itself, furniture, partitions, maybe around 0.27 inches. That part gets multiplied by the creep factor over time.
Ah, I see.
So when you add it all up, the immediate short-term sag, plus the immediate long-term sag, plus the crept long-term sag, the total estimated long-term deflection for our 15-foot span could actually reach almost 3/4 of an inch, maybe around 0.7 inches.
Wow, okay, that's significantly more than the initial deflection.
It is, and that's why designers have to rigorously check these total long-term deformations. You definitely don't want a floor that looks perfectly flat on day one, but then visibly sags after a few years. That can cause problems, like doors sticking or finishes cracking.
Yeah, that makes sense.
And frankly, many projects aim for better performance than just the bare minimum required by building codes, especially regarding visible sag.
Right, aiming higher. Okay, so we've covered strength bending and shear, and we've covered deflection, both immediate and long-term creep. But what about that bouncy feeling you mentioned? That's vibration, isn't it?
Exactly. Vibration criteria for CLT floor span is the next big piece, and it's all about occupant comfort. Like we said, nobody wants to feel like they're walking on a trampoline, especially in an office or apartment.
Definitely not. How do they check that?
Well, one common approach designers use comes from a Canadian research group, FPI Innovations. They provide what's called a base span limit based on the panel's properties.
A limit for how long the span can be before it might feel bouncy.
Pretty much, yeah. For our specific 5-ply CLT panel type, that calculated limit might be around, say, 16.7 feet.
Okay. And our example was a 15-foot span.
Right. So since our 15-foot span is comfortably below that 16.7-foot recommended limit, that's a good sign. It suggests the panel itself shouldn't have excessive vibration issues.
That's good news.
Now, it's important to remember, this check is primarily for the CLT panel itself. You still need other checks for the entire supporting frame, the beams, the columns, but it's a key first step for the panel.
Got it.
We can also calculate something called the natural frequency of the floor. For our 15-foot example, this might come out around 6.8 hertz. That frequency is another key indicator designers use to gauge how it will perform vibration-wise.
Hertz. Okay, so that whole example is for a simple single span, right? Just supported at two ends. But real buildings are often more complex. Panels might stretch across multiple supports. How does that multi-span layout change things? Does it add a lot of complexity?
Oh, it definitely changes things. It has complexity, yes, but it can also sometimes make things more efficient. The way forces like moment and shear distribute across the panel changes quite dramatically when you have multiple supports compared to just a single span.
How so?
Well, for instance, the maximum shear force can actually be higher in a double span setup compared to a single span of the same length. Even if the maximum bending moment might be similar or even lower in some spots, the reactions at the supports also change.
Interesting. So it's not always better to have more supports, necessarily.
Not necessarily simpler from a peak force perspective everywhere. It really depends on what you're looking at: moment, shear, deflection. This leads to a really clever and practical design strategy that engineers often use.
Oh, yeah. What's that?
Well, sometimes, early in the design, you might not know the final exact layout of every single CLT panel. Will this panel be a single span? Will it be the end span of 3?
Right, things might shift.
Exactly. So what designers often do is design the CLT panels themselves as if they were just single spans. But then, for the interior support points the beams or walls between spans, they design those to handle a potentially higher load, often about 25% higher reaction than a simple span would give.
So they design the panel for the simple case, but beef up the supports just in case it ends up in a multi-span situation with higher loads there.
Precisely. It builds in a safeguard. It gives flexibility for the final panel layout later on without needing to completely re-engineer everything if the layout changes slightly. It's a smart way to stay robust while simplifying the initial panel design a bit.
That is a really ingenious workaround for dealing with uncertainty early on. Okay, and speaking of multi-span, how does that affect the vibration performance we just talked about? Does having multiple spans help with the bouncy feeling?
That's a great question. And yes, it often does. Here's another fascinating insight. For multi-span CLT panels, especially continuous ones, designers can often recommend or justify a 20% increase in that base span limit we discussed earlier.
A 20% longer span for the same vibration performance? Why?
It often comes down to continuity, but also the presence of non-structural elements. Things like partition walls sitting on the floor, heavy floor finishes, or even rigidly attached ceilings.
Things that aren't part of the main structure but add stiffness or mass.
Exactly. These elements, even though they aren't the primary load-bearing structure, add an enhanced stiffening effect and damping to the overall floor system. This really helps dampen vibrations.
So in our 15-foot span example.
Right. If that 15-foot span was part of a multi-span layout or had significant partitions on it, its effective vibration limit might jump from 16.7 feet up to maybe 20 feet or so, 1.2 times 16.7.
Wow.
Which makes our 15-foot span seem even more conservative, even more compliant and likely to feel comfortable.
So engineers are cleverly leveraging the entire building system, not just looking at the bare panel in isolation. That makes a lot of sense. Okay, are there scenarios where things get even more intricate, where these standard checks and beam analogies maybe aren't quite enough?
Oh, absolutely. For sure. When you get into situations with really significant cantilevers sticking way out, or maybe where adjacent spans have vastly different lengths or unusual loading, then a more rigorous, detailed analysis is definitely appropriate. It's a must.
What does that involve? Like supercomputers?
Sometimes. It might involve using more advanced beam theories, like Timoshenko beam analysis, which explicitly accounts for those shear deformations much more precisely than the simplified methods.
Okay.
Or you might move to sophisticated finite element analysis, or FEA.
FEA. Heard of that.
Right. These are powerful computer models where you break the panel down into tiny virtual pieces. It allows engineers to model the panel as a complex plate, not just a beam. It can even capture how forces spread out in 2 directions across the floor, which simple beam math can't do.
So that gives a much more detailed picture.
Exactly. These advanced tools are really essential when you're pushing the boundaries of design or dealing with complex geometries and loading.
Wow. We have really gone on quite a journey today. I mean, from the basic building blocks, the panels, the girders, through all these essential checks for strength, bending, shear, then diving into how floors feel, the deflection, the creep, the vibrations, and even exploring these complexities of multi-span designs and advanced analysis. It's just incredible how much engineering depth there is in something as seemingly simple as a floor.
It really is. And I think this deep dive, it shows how designers have to blend these fundamental mechanical principles with really practical insights, rules of thumb, adjustment factors, to make sure these CLT panels are not just structurally sound, but that they also perform beautifully and, importantly, feel comfortable and solid for everyone using the space,
Oh.
all while navigating all these different real-world design scenarios and uncertainties.
You've definitely just received a shortcut to being well-informed on a really critical aspect of mass timber construction. And, it makes you wonder if there's this much unseen engineering going into the floor right beneath your feet. What other hidden complexities might be at play in the everyday structures all around us? And how might understanding just a little bit more about them empower you to see the built world with maybe new eyes? Something to think about. Thanks for diving deep with us.